So, good morning. Welcome to Krishna's classroom. In the last lecture, we introduced what are called measurable functions. In fact, we ended the talk with the definition of the measurable functions. Before that, we proved a theorem which gave four conditions which are equivalent to one another, which essentially helps us to test what is called the measurability of a function. Now, what we are going to do in this talk is to get more conditions or investigate more conditions for measurability and thereby identifying some of the classes of functions which we would normally like to get measurable, because our eventual objective is to define integral, and in the last lecture we gave an outline of our plan of action. Okay, so this is what we are going to do. So one of the conditions that we have for measurability of the function is this: f is from a measurable subset E of R to, we are taking it as this one, or it could be even an extended real valued function. That is, this means it is essentially the entire set of real numbers union minus infinity this is what you call the extended real value. And we said that one of the conditions for measurability is that for every C belonging to R, we have X belonging to E, and remember we are assuming E measurable. E is a measurable subset. So E is the domain of measure. Now there are three other equivalent conditions. Which would eventually help us to say that f inverse of any interval in the range is measurable. Okay, so we shall make use of these equivalent conditions to prove the rest of the things. So let us now prove the second theorem. We are making further investigations of what measurability means. Let define on a measurable if and only if, that is another equivalent condition for measurability. For every open set O F inverse of O, which consists of all those x belonging to D, for which fx is measured. Now what we are doing here is that describe the measurability in terms of what the inverse of the inverse of the function does on open subsets of the range. So let us prove this. Assume F inverse of O open is measurable for all open O. Then this implies F inverse of C infinity is for every C belonging, because they are all open sets. Okay, and this implies by theorem 1 the measurability of that. So that is one part. Now the other part is that assume F is measurable. Then we have to show that F inverse of O is measurable. Okay. Now assume Now assume, let's then what we have is O is the union of in fact a countable collection of open intervals. Now ik, each ik can be written as AK intersection BK, where AK is equal to and BK minus infinity to BK, and further you have so that ik is equal to assume now since f is measurable, since f is measurable, assume since f is measurable, we have f inverse of bk and f inverse of ak are measurable subsets. Are measurable subsets. And the measurable subsets forms a sigma algebra, form a sigma. Therefore, F inverse O is measurable since F inverse of union k equal to 1 to infinity is equal to now F inverse of Bk is measurable, F inverse of Ak is measurable, therefore their intersection is measurable, and therefore you have what you call F inverse of Bk intersection F inverse of Ak is measurable, and their countable union is measurable. Okay, that's all. Okay, so that completes the proof of that. So we have characterized the measurability of a function in terms of what it does, or in terms of pre-images of what are called open subsets of the page. Okay, so the nature of the pre-images of the subsets of the page. Now it must be pretty clear from what we were trying to do earlier, all these things. Now next theorem, here the question that we wanted to solve is this collection sufficiently large, right? Or do you get some of the functions on which we want this to work included in your measurable class of functions? So this is the next result, which says that all continuous functions are measurable. So you have, that is one of the first checks that you normally do, whether continuous functions do get into your working scheme. Okay, so let us do it. Let us prove this here. A real valued function continuous on its measurable domain. Is measurable. So all continuous functions on measurable domains are measurable functions. So we have a sufficiently large class of functions which are measurable. So let us prove this result. let E be a measurable set and let E be the domain of a measurable of a continuous, and F be continuous Now what we do is we take, let O be an arbitrary since F is continuous. The inverse image of F or inverse image of open sets under F is going to be open in E. Okay, that's what you mean by it's a continuous function. So we use that topological fact. F inverse of topology of E. That is F inverse of O is equal to E intersection some open set U, where U is an open subset of therefore this is open. That means E union now E is open, E is measurable, and U is therefore E intersection is because the measurable collection of sets form a algebra, or here only algebra is required. Consequently, by theorem 2, F is so this theorem is significant in the sense that The class of measurable functions is a huge class. Okay? Contains all the continuous functions. Okay? Therefore, whatever theory that we are going to develop is going to be applicable to what are called continuous functions. Okay. So remark. Theorem 3 assures that all continuous functions in measurable on measurable sets are measurable. So it's a very large class of functions which is measurable. Now this is a very nice consequence. That is, the class of measurable functions is large. The class of sets is now we use this define what is a monotone. Just recall a real valued function is either increasing or decreasing are called monotone. So you have what is called the monotonically increasing function and the monotonically decreasing function. Now we show that, see, a monotone function need not be a continuous function. Okay, right? Nor the other way around. So theorem a monotone function defined on an interval is measured. All monotone functions defined on intervals are measured. So you can see this, because this is, suppose we take a monotonically increasing on some interval. Suppose you take a monotonically increasing function. Then what happens? See, you are, suppose this is y equal to f of, this is the interval. Now what happens is you take c. Now what about f inverse of c? F inverse of c consists of this portion. Okay? So you see that because of the monotonic increasing nature, you see that it is starting from f inverse of c. This is f inverse of c. Okay. So you would assume f is monotonically increasing. Now you see that let E be then what you have is the set of all x for which fx greater than c. This is the same as the set of all x for which x is greater than f inverse of c. And you see that this is measurable. This is measurable means this is measurable. Therefore, f is measurable. And that really proves the result. Okay, right? Similarly, if it is monotonically decreasing, similarly, you can prove f is assumed to be monotonically decreasing. Okay, so that proves it. So monotone functions defined on intervals are all measurable functions. So you see, it's a huge class of measurable functions where you can comfortably develop the integration theorem. So the next theorem is introduces what is called the almost everywhere concept. So let an extended real value on a measurable set. Then first statement is that f is measurable on E and f equal to G almost everywhere on E, then G is measurable. Now this is the fourth theorem. Okay. Oh, sorry. This is the fifth theorem. Then the second contention is that for a measurable subset, D of E, f is measurable on E if and only if the restrictions of on T and its complement E, that is E slash T, are measurable. So we prove these two results. Okay, let us prove this result. First, let A be the set, a subset of E, or X belonging to E, for which Fx is not equal to and what more we are assuming? It's almost everyone. And on E and That means we are assuming that the measure of A equal to 0, and of course A is therefore measurable, E is measurable, and you have, so what we are trying to prove is the following. Now we know that G differs from F on A. Everywhere else F and G are the same. Okay. So what you, okay, let me do a Venn diagram for this purpose. See, you have E here, and then you have A here. A is where Fx is not equal to Gx, and the measure of A is 0. Okay, and here Fx is equal to 1. That's that's the situation. That now what do we want to prove? It is given that measure of A is equal to 0. Now we want to investigate whether, so what we want to, G is measurable or not. So let us look at this set of all x belonging to E, for which let be arbitrary. So C is a real number which is arbitrary. Now we look at this set. This set we break up in the following. Okay, right? To see that it may spill over A, some portion. So what you have is this. This can be written as the set of all x belonging to A for which Gx greater than C union what Gx x belonging to E slash A okay. Therefore, what is this? This can be written as and on this you see F is the situation. So what you have is write this as union Fx is greater than C, because on E slash A Fx is equal to Gx. Now this I can rewrite as This I can rewrite as union x belonging to E, fx greater than C, intersection E slash. Okay. Now that we will. Now you see, since f is equal to g almost everywhere, we were successfully when we could replace the on this portion. See, on the second place, the g could be replaced by. Okay, so that's what we. Now we look at these sets. Now you see that this is a subset of A and measure of A is 0. So because every subset of a set of measure 0 is measurable. What about this? Obviously, see, x belonging to E, fx greater than C is measurable. That is clear. And E slash E is measurable. Why? Because E is measurable, A is measurable. Therefore, this is measurable. What does this mean? This implies that is G is a measurable. This is significant. This part of the result is significant in the sense that if you have a measurable function f and if you allow or if you take a new function g which differs from f only on a set of measure 0, then that g is also okay. So you see that if you have a continuous function when it is measurable, then you allow discontinuities on a set of measure 0, then you see the new function that you construct is also a measurable function. Okay. So it actually enhances the class of functions which are measurable. Okay. Now let us look at the second part. So what exactly is this? Let us work it out. So you have This is the class on which and you see that there is a this is the subset on which fx equal, so this is A. Now this is the set on which inside A. Therefore, you see that look at this class. This is the place where we have this happening, and this is a measurable set. So this is a subset which is measurable, this is a subset which is measurable, this is a subset which is measurable, therefore, see, mean of these two is measurable. Okay, now part 2. First part, assume f restricted to D and f restricted to where both are measurable sets. Now what we want to work on is that f is measurable on. So let us compute x belonging to E this is equal to fx is greater. Now we have assumed that f restricted to D is measurable, f restricted to E slash D is measurable. Therefore, these two are measurable sets. These two subsets are measurable. Therefore, their union is measurable. Okay. So this is what you have. D. Then this is your D. This is where we are assuming that this part is measurable. That is, f restricted to E is measurable and f restricted to D is measurable. Therefore, you see that these two subsets are measurable. being the union of two measurable sets. Now what we want to work on is this, that is we assume D is a measurable subset of. E is already measured. Okay. And F is then you see that X belonging to D we are testing the measurability of F. This is equal to and D is measurable, this is measurable, therefore their intersection is measurable. Similarly, one can work with E slash D. Similarly, one has that is now these are useful tools in our later work. Okay, so let me conclude today with this theorem, and after this we will look at the structure of the class of measurable functions. Okay, so that will be our next theme. So we take all the measurable functions and see what properties hold for. So questions like whether sum of measurable functions is measurable, scalar multiple of measurable functions is measurable, whether what you call product of two measurable functions is measurable. Now these are the sort of questions that we looking forward to address in the next lecture. Okay, thank you very much.